Is Earth being watched by something not of this world?
You now say this is not only an alien spaceship, but it's nuclear powered? Why are you saying that?
The sun's magnetic poles flipped, officially marking solar maximum. At that exact moment, an interstellar visitor screaming through space at 137,000 miles per hour got blindsided by a billion-ton plasma bomb launched directly from our star.
The object, now officially named 3I Atlas, is believed to be up to 12 miles wide.
The object looks strange. It reflects a lot of sunlight, and from that, one infers that the diameter is 20 kilometers.
This is 3I Atlas, only the third known object from another star system ever detected. What happened when these two cosmic forces collided? And what does it mean for the technology you're using right now?
Well, you look at wind patterns. It turns out that many of these sightings, these objects defy the direction of the wind. These objects can go against the direction of the wind.
The interstellar intruder, hit by a billion-ton plasma bomb. This actually happened. An object from beyond our solar system, traveling faster than anything we've ever built, just took a direct hit from one of the most violent phenomena our sun can produce. 3I Atlas was discovered in Chile back in early July 2025. From the start, this was unusual. Its chemical makeup doesn't match any comet we've studied. It has significantly more carbon dioxide than water, which is the opposite of what we observe in comets formed in our solar system. Harvard astrophysicist Avi Loeb started asking uncomfortable questions. The trajectory looked too perfect. 3I Atlas passes suspiciously close to Jupiter, Mars, and Venus. Loeb called it remarkable fine-tuning. He even suggested, and NASA pushed back hard on this, that it might be some form of extraterrestrial technology. Most scientists think that's a stretch, but the path is genuinely bizarre. Here's what we know for certain. 3I Atlas is massive. Loeb's calculations put it at over 33 billion tons, measuring at least 3.1 miles across. Compare that to Oumuamua, the first interstellar visitor we detected back in 2017. That thing was maybe a quarter-mile long. 2I/Borisov, the second visitor discovered in 2019, measured about 0.6 miles. 3I Atlas is a damn beast. Then earlier this week, the sun launched a coronal mass ejection straight at it. Think of a coronal mass ejection as a billion-ton bomb made of plasma and twisted magnetic fields, traveling at millions of miles per hour. When these things hit planets or comets, the results can be catastrophic. We've seen this before with comets from our solar system. Back in April 2007, NASA's Stereo spacecraft watched as a comet called Encke got nailed by a wave of solar material. The comet's tail just disappeared. Gone. Within minutes, though, a new tail formed and Encke kept going. But 3I Atlas isn't from here. Its composition is alien in the most literal sense. How does matter from another star system react to a direct plasma strike from our sun? Nobody knows. The European Space Agency scrambled every available spacecraft to watch. Two Mars orbiters, Mars Express and ExoMars Trace Gas Orbiter, tracked the comet between October 1st and 7th from about 30 million kilometers away. Now the Jupiter Icy Moons Explorer, called JUICE, is moving into position to observe around November 1st. That date matters. November 1st is when 3I/ATLAS reaches perihelion, its closest approach to the sun. Solar radiation will hammer the comet at maximum intensity, vaporizing ice and potentially revealing its true chemical composition. If the chemistry matches comets from our solar system, it suggests planetary systems across the galaxy might share similar building blocks. If it doesn't, we're looking at exotic ingredients forged around a completely different star. Next week, this interstellar visitor passes within 1.67 million miles of Mars. That's incredibly close in cosmic terms, And all of this is happening while our sun just completed something it only does once every 11 years. But here's what nobody's talking about. Isn't the timing of this collision too much to be all random? What happens when the sun's north becomes south? On October 15th, NASA confirmed what space weather experts had been watching for months. The sun's magnetic poles have flipped, and solar maximum has officially arrived. Let me be clear about what this means. The sun's magnetic field doesn't just weaken or strengthen, it completely reverses. Magnetic north becomes magnetic south. South becomes north. This flip happens roughly every 11 years, and it marks the midpoint of what scientists call the solar cycle. The discovery of this cycle goes back to the late 1700s. Astronomers noticed something strange about sunspots, those dark patches visible on the sun's surface. Instead of appearing randomly, sunspots followed a pattern. Their numbers grew and shrank over approximately 11 years. At first, astronomers thought this was just about counting spots. They were wrong. As technology improved throughout the 1900s, scientists discovered the cycle involved the sun's entire magnetic field. The field builds up, tangles, reverses polarity, then builds up again. This process drives everything: sunspots, solar flares, coronal mass ejections, solar wind. All of it ties back to the magnetic field's behavior. We're in solar cycle 25 right now. When this cycle started in December 2019, scientists made predictions based on decades of data. They forecast a peak. Around July 2025, with roughly 115 sunspots at maximum. They expected solar cycle 25 to be weak, possibly even weaker than cycle 24, which had been one of the quietest cycles in over a century. A sunspot appeared on the sun's eastern edge. Nothing unusual at first, just another spot among thousands that appear and disappear throughout a cycle. But over the next few days, this sunspot swelled to 17 times the size of Earth. Scientists labeled it Active Region 3664. Massive X-class flares erupted from its surface. Some were so powerful, they triggered coronal mass ejections aimed straight at our planet. The result was the most powerful geomagnetic storm Earth has experienced in 500 years. A week later, a G4 geomagnetic storm slammed into Earth. Skies lit up with auroras, radio communications got disrupted across multiple continents, and NASA finally made it official. Solar maximum has begun. Here's the terrifying part. We won't know when we've hit the actual peak until months, possibly years afterward. Scientists need to watch activity decline consistently before they can pinpoint the true maximum. The worst could still be ahead of us. And this is the environment 3I Altus just wandered into. An interstellar object from another star system arrived at our solar neighborhood precisely when our star decided to flip its magnetic field and enter its most violent phase. The coincidence seems impossible, but there's a historical pattern that makes it even stranger. The 70-year mystery that made rivers freeze in summer, the sun has gone silent before. Twice in recorded history, it essentially stopped producing sunspots for decades. Both times coincided with periods of inexplicable cold that reshaped human civilization. Nobody can explain why it happened. Between 1645 and 1715, 70 years, sunspots virtually disappeared. Astronomers across Europe kept meticulous records during this period. They documented only about 50 sunspots across the entire 7 decades. In a typical 11-year cycle, thousands of sunspots appear. Scientists call this the Maunder minimum, named after the astronomer who studied it extensively. But here's the kicker. During this exact time frame, Earth experienced what historians call the Little Ice Age. Rivers that rarely froze became solid ice. The Thames in London A river that historically stayed liquid year-round froze so thick that people held frost fairs on its surface. Markets, games, even ox roasts happened on the ice. Europe faced brutal winters that killed crops, starved populations, and toppled governments. We can't definitively prove the sun's silence caused the cold. Other factors likely contributed: volcanic eruptions, ocean current changes, and variations in Earth's orbit. But the correlation is impossible to ignore. 70 years of minimal solar activity. 70 years of harsh cold. The timing matches too perfectly to be a pure coincidence. Then it happened again. The Dalton minimum ran from roughly 1790 to 1830. Once more, solar activity dropped well below normal. Once more, global temperatures plummeted. Mount Tambора's catastrophic eruption in 1815 threw so much ash into the atmosphere that it created 1816's Year Without a Summer. Crops failed across Europe and North America. Food shortages triggered riots. People in New England reported snow in June. Frost killed crops in July. It was a climate disaster, and the sun's reduced activity likely played a role. Fast forward to 2008. Solar cycle 24 began, and it was weak. Sunspot numbers fell below average. Some researchers started asking uncomfortable questions. Are we heading toward another grand minimum? Could the sun be preparing to go silent again? Then solar cycle 25 arrived and shattered every expectation. Instead of continuing the downward trend, the sun exploded with activity. Sunspot numbers more than doubled predictions. X-class flares multiplied. Coronal mass ejections launched at rates nobody forecast. What changed? Why did the sun suddenly wake up after a weak cycle? Why does it sometimes go silent for decades, then roar back to life? Nobody knows. But before we worry about the sun going quiet, we need to understand what happens when it gets angry. When telegraph operators talked on aurora power alone. Let me tell you what the sun is actually capable of when it enters full rage mode. The historical record reads like fiction, except every detail is a documented fact. September 1st and 2nd, 1859. British astronomer Richard Carrington is observing sunspots through his telescope when he sees something nobody had witnessed before: a massive bright flash on the sun's surface. He's watching a solar flare in real time, though he doesn't know what to call it yet. Hours later, a coronal mass ejection, the billion-ton plasma bomb I mentioned earlier, slams into Earth's magnetic field. This is the Carrington event, the gold standard for solar destruction. Telegraph systems across Europe and North America lose their minds. Operators report receiving electric shock severe enough to knock them back from their equipment. Some telegraph lines catch fire. But here's the weird part. Other operators disconnect their batteries completely, and their machines keep working. The storm's induced electrical currents are powerful enough to run the telegraph systems by themselves. Two operators working the line between Boston and Portland managed to communicate for 2 full hours using zero battery power. Just the aurora. They even note in their records that the signal is clearer than when they use their regular batteries. Jump forward to May 1921. The New York Railroad storm hits. This is the most intense geomagnetic storm of the entire 20th century. It caused a fire at a railway station in Brewster, New York. Railroad signaling systems across the northeastern United States fail. Trains can't communicate their positions. The chaos ripples through the transportation network for days. March 1989. This is when modern civilization learned exactly how vulnerable it is, early 2022. SpaceX launches a batch of Starlink satellites. A solar flare generates geomagnetic storms that increase atmospheric drag just enough that 40 of these brand new satellites can't maintain orbit. They burn up on re-entry. 40 satellites, each worth hundreds of thousands of dollars, were gone because the sun had a moderately bad day. Now scale that up to everything we depend on. GPS navigation for planes, ships, cars, and phones. Telecommunications satellites. Weather forecasting systems. Financial transaction networks. Military reconnaissance. Scientific research platforms. We've got thousands of satellites in orbit, and every single one is vulnerable. Estimates put the cost of a Carrington-class event today at $600 billion to $2.6 trillion in the United States alone. But that number doesn't capture the real impact. What happens when GPS fails and planes can't navigate? When telecommunications collapse and emergency services can't coordinate? When power grids across entire continents go dark for weeks or months? Food distribution stops. Medical equipment fails. Water treatment plants shut down. The cascading failures would ripple through every system that assumes electricity, and satellite connectivity will always be there. We're driving through a cosmic shooting gallery during solar maximum, and we just watched an interstellar comet take a direct hit. Which raises the question, what actually happens when these plasma bombs strike? Why the sky is burning green, and what it means for your phone. Something extraordinary is happening in Earth's skies right now, and it's directly connected to what just happened to 3I Atlas. Understanding this connection requires grasping what occurs when solar plasma collides with matter. When 3I Atlas approached perihelion earlier this month, astronomers observed it becoming extraordinarily bright. Most of that brightness is concentrated in the green part of the visible spectrum. That green glow comes from diatomic carbon, C2 molecules, getting energized by solar ultraviolet radiation. When ultraviolet light hits these carbon molecules, they emit that distinctive emerald color. It's the same physics creating green auroras on Earth. Different matter, same principle. We typically think of auroras as green. This happens when solar particles collide with oxygen molecules at altitudes between 100 and 300 kilometers. The oxygen atoms get excited by the collision, then release that energy as green light. But the May 2024 storm produced something different. Dramatic red auroras. These form when particles interact with oxygen even higher up, between 300 and 400 kilometers. At those altitudes, the oxygen is more spread out, and the physics changes slightly. Instead of green, you get red. Here's the kicker. For red auroras to be visible to the naked eye, they need to be at least 10 times brighter than green auroras. The fact that people around the world saw red auroras in May means the storm's intensity was genuinely extraordinary. Reports came in from the Caribbean, Mexico, Southern Europe, places that almost never see auroras. The lights reached latitudes where they exist only in ancient myths and historical records from centuries ago. Every aurora you see is beautiful. Every aurora is also a warning. When those charged particles stream down Earth's magnetic field lines, they don't just make pretty lights. They create electrical currents in the upper atmosphere. These currents induce voltages in power lines, pipelines, railroad tracks, anything long and metallic that crosses the landscape. In Quebec in 1989, these induced currents were strong enough to collapse the entire electrical grid. Your phone's GPS is experiencing interference right now if auroras are visible. The charged particles in the upper atmosphere disrupt the radio signals traveling between GPS satellites and your device. Sometimes, the error is just a few meters. During intense storms, it can be tens of kilometers. Planes flying polar routes have to reroute because GPS becomes too unreliable for navigation. NASA's Artemis mission guidelines are explicit. Do not launch near solar storms. The risk isn't just from the dramatic events. It's from high-energy particles that can fry sensitive electronics and disrupt radio communications. If contact with a spacecraft gets severed during a critical phase like landing or docking, the mission fails. Astronauts could die. But there's a paradox buried in all this danger. During periods of high solar activity, the sun's magnetic field strengthens and expands. This enhanced field shields Earth and its satellites from galactic cosmic rays, high-energy particles originating from exploding stars in distant parts of our galaxy. These cosmic rays cause gradual, cumulative damage to electronics over time. Solar Maximum offers extra protection against them. Satellites are less vulnerable to long-term cosmic ray degradation when the sun is active. It's a cruel trade-off. Protection from deep space radiation, but increased vulnerability to solar radiation. Spectacular auroras and scientific opportunities, but heightened risks to the infrastructure we depend on. The European Space Agency's decision to deploy multiple spacecraft to observe 3I Atlas during solar maximum isn't just about studying an interstellar visitor. It's a test. Every successful measurement proves we can maintain observations under adverse conditions. Every failed sensor or corrupted data stream warns us about vulnerabilities we haven't addressed. Which brings us to the question nobody wants to ask directly. The answer: nobody expected about climate. Here's what everyone's thinking, but almost nobody asks. With solar maximum raging and global temperatures climbing year after year, is the sun cooking our planet right now? The answer is going to surprise both sides of the climate debate. During solar maximum, there is an increase in total solar irradiance. That's the amount of solar energy reaching Earth. The sun does put out more energy when it's active. This causes measurable fluctuations in Earth's climate system. But notice the word I didn't use: significant. The variations are relatively small. The difference in solar energy output between solar maximum and solar minimum is roughly 0.1%. 0.1%. That's not a typo. Here are the numbers that matter. The amount of solar energy Earth receives has followed the sun's natural 11-year cycle, with no net increase since the 1950s. Scientists have precise measurements going back decades. The solar cycles tick up and down, but the baseline hasn't changed. Over that same period, from the 1950s until today, global temperatures have risen markedly and consistently. The warming trend doesn't follow the solar cycle. It just keeps going up while the sun oscillates. The data make it unambiguous. Solar activity hasn't been the primary driver of observed global warming over the past half-century. This doesn't mean the sun is irrelevant to climate. Solar cycles do cause temperature variations. But those variations are measured in fractions of a degree Celsius. They're real, they're measurable, and they're swamped by other factors. The Maunder minimum and Dalton minimum offer interesting counterpoints. Both extended periods of very low solar activity coincided with cooler global temperatures during the Little Ice Age era. This suggests that prolonged solar minima might contribute to cooling effects. What about Solar Cycle 25's unexpected strength? We're seeing the most active solar cycle in over 20 years. Could this supercharged activity push global temperatures higher? The physics says no. The increased energy output during this solar maximum is still only that 0.1% variation. It's not enough to significantly move the needle on global climate trends. This is actually good news for solar scientists. It means we can study solar maximum without worrying that we're about to trigger runaway warming. It also means we can't point to the sun as a solution or scapegoat for warming that's clearly happening from other causes. The real climate threat from solar maximum is indirect. Geomagnetic storms can disrupt or destroy weather satellites and climate monitoring systems. These satellites provide crucial data about temperature, ice coverage, atmospheric composition, ocean currents, all the measurements we need to understand how the climate is changing. If a major Carrington-class storm knocked out key observation satellites, we'd lose crucial information. The sun's threat to climate science isn't through heating Earth directly. It's through blinding our ability to measure what's happening. What happens to 3I Atlas over the next few weeks will tell us something about how matter from other star systems behaves when exposed to our sun's fury. Whether its composition matches anything we've seen before. Whether the fine-tuned trajectory Avi Loeb keeps talking about is just a cosmic coincidence or something stranger. Your GPS might glitch. Your phone's compass might spin. Power grids might experience induced currents that operators have to actively manage. And somewhere overhead, satellites are taking radiation hits that gradually shorten their operational lives. The sun flipped its magnetic field. An interstellar object got hit by a plasma bomb. And we're all living through the cosmic consequences right now, whether we're looking up at the sky or not. Will 3I Atlas survive its close encounter with the sun, or will we watch an interstellar visitor disintegrate in real time? And are you prepared for the day your GPS stops working because the sun decided to throw another tantrum? Let us know what you think. Remember to like, share, and subscribe for more. Also, click the next video showing on your screen. You will enjoy it.